Alright, in this video we're going to see which thickness we have to give our fins so it can withstand, well, the normal forces. So, of course, the fins at an angle of attack, there's going to be a bending moment over the root, alright? And, well, this moment, to withstand this moment, Fleaman has a model. It's writing kind of strange, isn't it? Give me a sec. Alright, I had a weird setting. Yeah, now it's better. So Fleaman has a model which is incorrect. No, I mean it isn't incorrect, but it's that he has a typo. It's in chapter 4. So there's a typo. Just be aware of that. I'm going to write it in the correct form. So the thickness we have to give the fin in the root is the following. The normal force. Let's put. Normal force, the maximum normal force. We're going to speak about what Fleaman puts here, times the aspect ratio, times this, over the ultimate strength of the fin, of the fin's material, and this over power 1/2. I think he leaves maybe one part out of the brackets accidentally, so everything is at the power 1/2. All right. Now let's talk about which Nmax Mr. Fleaman uses. He uses the total normal force for a cruciform setup. So if we extrapolate this to any amount, any number of fins, we're gonna have to add let's see, yeah, sorry, so the correction for this, extended to any amount of fins, we put n here. Sorry, it's the same variable name, but this is the number of fins. So, oopsie daisy. Of fins. Okay, and this is a maximum normal force we want the fins to withstand. So yeah, you can dimension your fins to withstand whatever Nmax you want it to withstand. So maybe, I don't know, there are many ways to think this problem. Maybe you could choose a certain angle of attack at a certain dynamic pressure. Well, that's up to you. Okay. I'm just gonna put on the table the basics of calculating all this, and then you do the engineering, of course. So the weight of one fin, you want to minimize this. Discuss this in a second. It's just the density of the material. So let's put of m, just not to confuse with the other densities, and the surface of one fin times the thickness. Just put T. So if we substitute all this and massage the equation a bit, we will arrive at the following. By the way, I'm gonna use my simplification of Cn alpha is equal to is it 3.2, if I remember correctly on the last video. well, not the last video. It's just never mind. The last video I did was on stability, not 2.4.2, but I think I was discussing this. So the simplified. Okay, let's see. Give me a sec, because I'm just realized that Nmax. Okay, I define Nmax differently from Fleeman. Sorry, I'm kind of messy with these explanations. As you know, I mainly improvise all this. So okay, and then this is the CN alpha for any amount of fins. And 4. Okay. Right, guys. I think I'm messing up a bit too much. Let's do it easier. Because I wanted it to split up. I don't like what I was doing. So this is the total normal force of all the rocket, not of one fin, because it's going to be, after all, it's just moving this N/4 up and down. So total of, sorry, not the whole rocket, of fin set. Okay, so the CN alpha of the fin set is this, and this is extended to any amount of n. All right, then remember there's like the final correction term, but this is, you know, the correction term from Open Rocket, but we'll discard just this right now. Okay, so let's see. If we put all this inside here, and we use this simplification, and we let's see if I've done any other simplifications. No, that's about all. Well, just note that Nmax. Oops, not M. Nmax, maximum normal force, is simply CN alpha times reference area times dynamic pressure times alpha, and the maximum of this. The maximum of this product, because CN alpha is going to be constant. And the reference area, of course, is going to be constant. So the maximum normal force is this, which is a constant, times the maximum of between this product. Okay. And I think that's about it. Just one more. Well, it's not a simplification, it's just the surface of one fin is simply the span squared over 2 times aspect ratio. And, well, I use, again, specific span, if you remember. It's just the span over the diameter. This is a variable I made up, which is very, very useful. Alright, if we put this in here, we'll find that the weight is equal to, put it in another color, because these terms here are going to be constant. So it's density of the material, ultimate strength or yield strength, depend on what you're designing, how you're designing. This is a design parameter, so we choose at which is like the maximum load we want the rocket to withstand. So remember, this we can choose, up to you if you're more conservative. Okay, then we have this constant here, and then we have the rocket's diameter cubed, and then we have by the way, this part is not on Fleeman. He does like a graph that, which I kind of don't like because, it compares. It tries to conclude like which fins weigh less. But what I'm gonna do here is I'm gonna compare for the same. Let me write this down because this is important. So I want to know. Yeah, I should have said this before. So for a same corrective moment, well, normal force, not quite. For the same n, which geometry weighs less, basically? So this is the question I'm gonna try to solve analytically with this analytical analysis. Analytical analysis I love so much. The analytical analysis that Fleeman does, kind of don't agree with it because he doesn't like fix. Well, yeah, he doesn't fix like how can I explain this? So if you check his analysis, let me check which page this is so you can take a look at it. Okay, it's page 304. He fixes the surface and the Nmax. Well, you can't really compare. How can I explain this? It's kind of intuitive, but for me, but I'm having trouble explaining it to you. So, what I want to see is, for the same conditions, for the same normal force, I want to know which geometry weighs less. But we have to be in the. I'm not going to compare, pineapples with bananas. I want to compare fins in the same conditions. So, what I impose is that the fins are going to be the same normal force, which is saying the same Cn alpha. That's right. So, never mind. So the weight of the fins are going to be all these constant terms, and then Cn alpha. This is, remember, the whole rocket. Power 3/2 times this. Power 1/2. So, if we have two fins that give the same, two fin sets that give the same Cn alpha, well, having a higher taper ratio is just gonna get the weight up. Do you get what I'm? Let's see if you can understand what I mean. So basically, two fin sets which make the same effect in terms of Cn alpha, may not in other terms, but in Cn alpha. So I'm not saying that they have the same surface, which is what Fleeman kind of does. I'm saying that they have the same lift, so the same, like, more or less the same restoring moment. Well, for the same effect, a lower taper ratio is going to get the weight down. And remember, for a same specific span and aspect ratio, if we get the taper ratio down until 0.3 or 0.2, it doesn't affect the Cn alpha. So this means for a constant specific span and aspect ratio, we're gonna want to get the taper ratio as down as possible, so up to 0.3 or 0.2. that would be ideal because it's not going to penalize the CN alpha, and we're going to have a lower weight. The only thing that's going to be penalized is I believe we're probably going to have a thicker root. So if we have, if we constrain with the root, well, lower taper for the same specific span and aspect ratio is going to give us a longer root, which could be a case which we are constrained by that, but I think it's interesting to put it in this way. Guys, I'm really sorry. I made an error here. Please forgive me. I should have looked this in more detail before doing the video. I'm sorry. So, if this is total force for the fin set, we have to put a 4 over n here. I promise if I mess up again, I'm just going to redo all this. I'm really sorry. So why is this? Imagine, so what Fleeman does, he doesn't put this term. But this M max, he always talks about cruciform, which is 4 fins. So if, for example, we have a cruciform that is, that gives 100 newtons of total N max, if we had the exact same fins, but instead of 4 we had 8 fins, then N max would be 2 times. So it would be 200 newtons. However, the T root, of course, is not going to be twice. Well, not twice because this is inside a root, but it's not going to be higher for having 8 fins, although N max is increasing because we have exactly the same fins, but we have 8 now. We just have the same fins, which should have the same T root because each one is withstanding the same amount of lift. So I left out this. I'm really sorry. So finally, this is going to be a little... Yeah, because I was thinking, where the N has to be around here. I don't know, intuitively the N has... the number of fins has to be somewhere here. So we have 2 here. Well, it's kind of ugly here, but... And then we'll have an N square root. Okay. Now it looks good. Okay, now that's much better. Okay, but there's a trick here. Because this is the weight for 1 fin. So if we put the weight for all the fin set, then we have to multiply by n again. Of course, because we have n fins. So this is now 3/2. I hope you followed me with all my mistakes. Okay, now that's better. Now this makes sense. So the total weight of the fin set is going to be n to the power 3/2. This means more fins for the same amount of lift are going to weigh more. So this is a very nice conclusion we can draw from this equation. So more fins, I'm going to write this because I think it's important. More fins same for equivalent. Let's put more fins, way more. Looks like kind of intuitive, but didn't have to be. Didn't have to be. Well, at least we proved that mathematically. All right. And then for the same for equivalent stability, when I talk about equivalent stability, please note I'm saying the same Cn alpha. It's not quite equivalent stability. Of course, I've discussed this in much more depth in the previous videos, but for now we're going to say that having the same Cn alpha is going to give the same stability, which is not a bad conclusion, or not a bad simplification. So for the equivalent stability, lower taper ratio weighs less. All right. Cool. I think that these are nice conclusions. What do you think?